In this video, we will start with chapter 10, which is on exponential and logarithmic functions. Section 10.1 deals with the nature of an exponential function. So assume we have the polynomial function x cubed plus x squared plus x plus 1. Here, our exponents are constants. But we can also have the exponential function where we have y equal to 2 to the power of x. Now our unknown is in the exponent. More generally, the exponential function y is f of t, and this is b to the power of t. So in this case, t is our exponent and our independent variable, and b is our base value. So if we look at some features of the exponential curve, the first feature is that it's continuous and smooth. That means it's continuously differentiable for an n number of times. It is strictly increasing and strictly convex. It has a range. The range of the function is limited to between 0 and infinity. This is regardless of the sign of t. Remember, t in this case is our exponent and unknown. Our exponential function is also strictly monotonic, or strict monotonicity applies, which means there's one-to-one mapping. So there's a unique value for each value of t. This means our inverse function is also monotonic, and our inverse function of the exponential function is the logarithmic function. You can express any positive value as a unique power of a base for any b larger than 1. So what does the generalized exponential function look like? So we have y, let me just change color here. Y equal to a b c to the power of ct. So we have a and c as extending or compressing factors. Or agents. So for our c value, our exponential function will have the same y-intercept, but it will be steeper or flatter, and for a, it shifts on the y-axis. So if we look at figure 10.2, we have y and x. So this would be y equal to ft equal to bt. If we change c, our y-intercept stays the same, but it becomes steeper, so this would be y equal to ft or gt, let's just give it another function name, equal to b2t, or a flatter curve would be y equal to ht equal to b 0.5t. What happens if we change the value of a? So again we have x and y. If we have y equal to ft equal to bt, this will be y equal to 2b. So our preferred base value is b equal to the natural exponent. This natural exponent e is equal to the value of 2.71828, and is an irrational value like pi. So in this case, we have y equal to et. The derivative of this exponential function is simply the same exponential function. What happens if we expand this to include our compressing and extending factors? So if we have a function like y equal to a or t, if we want to take the derivative of this, we use the chain rule. The chain rule. So we set y equal to a EW, W is equal to RT. That means dy dt will be equal to dy dw times dw dt. We know that this is simply EW times A. Product rule will tell us the derivative of A with regards to W is 0, so it falls away, times the derivative of W with regards to T is simply R. So we are left with A or EW. We want it with regards to T, so we simply replace W with RT.